Okay, now how do I convert this voltage? Let us say this is a voltage. I mean, you can now use your innovation to think about how do I convert a number into a binary number. Very simple. Any ideas? I will give you a hint. I can measure time accurately. So, if you have that hint with you, first thing I need to do is somehow convert the voltage into time. And then I can measure the time, and in that time I can measure how many pulses have gone in that time, right? And if I count the number of pulses, the count is equal to the binary number. So, very simple idea. So, first step is you need to somehow convert the f of n into a equivalent time linearly related to it. And what is the waveform which has a linear relationship between the time and voltage? You have seen that waveform in the last classes. A sawtooth waveform. A sawtooth waveform has a relationship time versus voltage is linear, right? So, if you have a sawtooth waveform, then the voltage will be converted into corresponding time. Larger the voltage, larger will be the time. Smaller the voltage, smaller will be the time. So, this waveform, if I use it as my part of the system, then I will be able to convert voltage into time. Normally, this voltage here is allowed to be between 0 to 5 volts. It is almost a standard, and that the A to D converters restrict the input voltage to be between 0 to 5 volts. 5 volts will correspond to the highest number and 0 correspond to the lowest number. That means, if this is 5 volts, this duration should, if this corresponds to 5 volts, there is a specific duration corresponding to this, and I can adjust this duration of course by using the different slope of this sawtooth waveform. Okay. So, now I have converted the voltage into linearly into this. When I use the word linear, I am meaning linear, meaning thereby that I do not allow any variations from the linearity. It should be exactly a linear curve. So, your sawtooth waveform must be as close to linear as possible. An exponential charging capacitor kind of an exponential, even if the time constant is very large, is not a good enough sawtooth waveform. So, how to generate this sawtooth waveform? The best way to generate a sawtooth waveform is to take a current source and charge a capacitor. The voltage across this will be equal to integral IDC, V is equal to integral 1 by C integral I dt, and I is constant as a constant current source. So, if we pull this out, this becomes I 0 by C dt, which is nothing but I 0 by C into T. So, I got a linear variation of this voltage with respect to time as I want. Of course, I shifted the problem to this now, and this fellow should be really a constant current source. In addition, the so called internal impedance of this should be ideally infinity. Otherwise, it will be again the same RC time constant problem will come. So, it should be very large. So, you must make a current source which is almost ideal and then use it for charging a capacitor. So, that is how we generate this waveform. I will give you another technique as we go along to get a better sawtooth waveform which is linear, but right now accept it. Most of the ways to generate sawtooth waveform is using this principle of charging a capacitor using a linear ideal constant current source. So, what I require here is a Anyway, so now how do I change it?
Excuse me, sir. How will you discharge it?
Pardon?
How will you discharge it to get the drop?
After the conversion is over, I short it and start for the next one. So there is a short circuit across it, and the short circuit closes when the conversion is over. So ready for the next one. Okay. Now the voltage may be anywhere between 0 to 5 volt. Highest value is 5, but voltage may be 3 volts, for example. So there must be a way of stopping this at 3 volts if the voltage is 3. So how do I stop a growing waveform at a given voltage between 0 and 5? Very simple. Comparator, right? You take a comparator and put this voltage here, and here you put a sawtooth. So it changes state when this voltage is equal to the 23 volts. When this reaches 3 volts, it will change its state. So you know when the values are equal, and that is the time you have now converted that 5 volt or 3 volts into a corresponding time. So the pulse width you get here change from the original state to the other state after the comparator gives the change in the state, will give you the width of the time. Are you with me or not? So initially it is sitting at one state. When this reaches equal to some point here, then obviously this will change the state. So the time between these two is what is equal to the time duration corresponding to this. So now I have a conversion from the actual voltage f of n to a corresponding time. Now how do I measure this time? Very simple. If this time duration, what I have obtained from this comparator, is used in the AND gate, this has the one input waveform, and the other one is a series of pulses like this. So the number of pulses that go through this time is equal to whatever is the number of pulses here. If this is a clock at 1 megahertz or some frequency, you know how many pulses have gone here within that time. So now you know what is the value of this time equal to. Are you with me or not? Within the time duration, I am counting pulses. How many pulses have gone in the duration equal to the width of this. So the number of pulses, and this interval is fixed. I said my 1 megahertz clock or 10 megahertz clock. So this interval is fixed. So the number of pulses into interval is equal to the t time, t that is there. So now I have set a number here which is directly related to, don't take this is not the same n as this, some k. This k is now, look at all the sequence, this k is directly proportional to f of n. Are you with me? If it is 5 volt, the duration will be longer, this much. So proportionately the voltage is low, the time duration will also be short, and accordingly number of counted pulses are also equal to a smaller number, and you count those pulses. How do you count pulses? Then you have something called a counter. We will read about it later. And this counter is a n-bit counter. So it goes on counting, changing its binary number, starting from 0, 0, 0. When 1 comes, it becomes 0, 0, 0, 1. When next one comes, it becomes 0, 0, 0, 1, 0, and so on and so forth. So it counts the number here, k, in terms of a corresponding binary number. Are you with me? This is the logic or the reasoning behind a simplest A to D converter. And what all I have used here is a ramp signal or a sawtooth signal, and so this is called a single slope A to D converter. Only one slope. We will see next something called a dual slope, but right now this is called a single slope.